Global climate change is one of those subjects in which it appears everyone has an opinion, independent of whether it's well informed. But as with many subjects, an understanding of the history is important for discussing the future. In fact, the Earth has undergone massive changes in climates at many times and on many timescales over its history. And I will not address directly today global climate change itself. I will address the history of climate change, the factors that influence it, and most particularly, the atomic historians we have to record it. The cyclical gravitational pulls and pushes of the Moon, the Sun, and the other planets cause changes in the tilt of the Earth's axis and the orbit of the Earth, which repeat on timescales ranging from 23,000 to 110,000 years. To see how these forces affect Earth's history, we need a record with a much longer memory than that of the tree rings. We have found such records in the ice of the polar glaciers and in the sediment of the ocean floor. The amount of sunlight falling on a particular region of the Earth has a major impact on that location's climate. This is a fairly obvious statement. The amount of sunlight falling in Antarctica is zero for half of the year, leaving it a cold and frozen place, whereas the amount of sunlight falling on the equator first doesn't change very much over the course of the year, but secondly is much more intense in that the sun's rays are much more direct and the amount of energy absorbed per square meter of atmosphere or ocean or land is considerably greater. Now, if the sun's energy output varies, this will change the amount of energy reaching the Earth. We discussed last time how the sun's output does vary over the 11-year sunspot cycle, but these variations have been measured as only 0.1% or perhaps a little more, too little to cause very significant change. Longer-term changes in the sun's output, while we have no direct measurements because they are only possible with satellites, are not excluded. The Little Ice Age and the medieval warm period we discussed last time correspond to respectively lower and higher sunspot numbers. And so it's possible that longer timescale fluctuations in the sun are also important. However, the dominant and predictable changes in solar energy input come from perturbations in the Earth's orbital parameters caused by the gravitational influence of the Sun, the Moon, and the other planets. The things that change are the direction the Earth's axis points in the sky, the amount of tilt of the Earth's axis compared to the plane of its orbit around the Sun, and the shape of the Earth's orbit. These are all determinable through direct astronomical calculations, which are remarkably precise. As we suggested last time in the timing of eclipses, we can do the calculations involved and predict exactly where each planet, the Moon, the Sun, and the Earth will be, and the relative forces acting on each of them over long periods of time. So let's start with the first and shortest of these perturbations to the Earth's orbit. The change in the position of the Earth's axis, where the north pole of the Earth, the axis around which the Earth is spinning, is pointing in the sky. This, it turns out, changes on a regular 23,000-year cycle. The Earth is spinning. It's like a top. It goes around 365 times in a single orbit around the Sun. Now, you've all probably spun a top as a child, if not more recently, and when you spin it, it starts spinning very rapidly, and the axis stays pretty stable. But gradually, as it starts to feel the strength of gravity trying to tip the top on its side, the orbit starts to do this. The axis, rather, of the top starts to do this. That motion we call precession. And just as the Earth's gravitational field on a child's top spinning on a table wants to tip it over, the mutual gravitational pulls of the Sun, the Moon, and the other planets tend to want to tilt the Earth over, and so it also, as it spins rapidly once a day on its axis, undergoes a slow precession every 23,000 years. Couple this with the elliptical orbit of the Earth around the Sun, and the seasons can be seriously affected. The Earth's orbit around the Sun is an ellipse. That is, it's a squished circle. And unlike one sees in some textbooks, the Sun is not at the center of that squished circle, but it's at what we call the focus, one of the 2 points which you'd thumbtack down a piece of string if you wanted to draw an ellipse with a pencil. As the Earth goes around this ellipse then, it alternatively gets closer to the sun and farther from the sun. And the change is not trivial, it's a few percent. Now today, we're closest to the sun on January 6th and farthest on the 4th of July. This may naively come as a shock to you because you all know that it's summer on the 4th of July and it's winter, cold, on January 6th. You might think we would be farthest from the sun then. But then you will recall that the Earth's seasons are not caused by this small variation in the distance between the Earth and the sun, but rather by the tilt of the Earth on its axis. When the Earth is tilted away from the sun is over here, its rays strike the surface indirectly, and each square meter of atmosphere, ocean, or land absorbs less solar energy. When the rays are more directly overhead, as they are in the southern hemisphere on our January 6th, more energy per square meter is absorbed. So again, today, we're closest to the sun at the peak of our winter, because the two effects, the tilt of the Earth's axis, which leads us to absorb less sunlight, and the distance from the sun, which leads us to absorb more sunlight, counteract each other a little bit, which means in the southern hemisphere, which of course has the opposite seasons, when they're closest to the sun, when the Earth's sun's rays are most direct, and they're farthest from the sun when the sun rays are least direct, has more extreme temperature changes. Antarctica is colder than the North Pole. This is true today, but this position of the Earth's axis rotates around every 23,000 years, meaning that at 11,000 years, the opposite situation will obtain. That is, we will be closest to the sun on July 4th, with our axis tilted towards the sun, so summer will be more intense, and we will be farther from the sun, receiving less energy, when the northern hemisphere is tilted away from the sun, so the energy we receive will be even less than we do in winter today. That is, we will have hotter summers and colder winters. But there's another important aspect of this elliptical orbit of the Earth around the sun. The Earth stays in its orbit because of the gravitational attraction between these two massive bodies. The gravitational attraction, you will remember from a lecture long ago, is greater when the two objects are closer to each other than when they're farther apart. Thus, the force the Earth feels in its orbit around the sun is greater when it's closer, and therefore it moves faster in its orbit. It bends more sharply, whereas over here, when it's far from the sun, it's moving more slowly. Thus, we will not only have hotter summers, but we will have shorter summers. And we will not only have colder winters, but we will have longer winters. And it turns out that latter effect becomes dominant. So that's the first effect, the position at which the Earth's axis is pointed in the sky compared to the shape of the Earth's elliptical orbit. The second effect that's important is the amount of tilt of that axis. How much is it tilted over? If the Earth were going around the sun and its axis were perpendicular to that orbit, then we would have no seasons. Or at most, we'd have modest seasons resulting from the change of the distance around the elliptical orbit. But the axis is tilted over, and the amount of that tilt also changes with time, from 22.1 degrees to 24.5 degrees, a greater tilt. That cycle takes 41,000 years. This, of course, also exaggerates and moderates, alternatively, the seasons. When the axis is tilted over more, the direct rays are greater at higher latitudes in the summer, and the indirect rays are even more indirect rather, in the winter, and so the seasons get amplified. Currently, and over the next 10,000 years or so, we're in a position where the Earth's axis is going from the 23.4 degrees it is today, closer to a line, to 22.5 degrees. Thus, we're in a cycle where the seasons are moderating. Finally, the shape of the Earth's orbit, the shape of that ellipse, the degree to which it's squished from a circle, also changes regularly because of the tugs and pulls of the other planets, the moon and the sun. The shape of the orbit goes from an almost perfect circle, only 0.5% out of perfectly round, to a rather extreme squished ellipse that's 5.8% away from a perfect circle. Now, these numbers may not sound like very much, but they're really quite significant, and you can see them very easily if I draw them to scale. A 0.5% thing looks very much like a circle. A 5.8% ellipse looks very much squished. In the circle, of course, the sun is close to the center. In the ellipse, the sun is off to one side. And so the variation as one goes around the orbit of the amount of solar energy reaching the Earth becomes significant. One cycle, going from round to squished to round again, takes about 100 to 110,000 years. This eccentricity today, also currently roughly between its two extremes, is actually decreasing, again leading to a moderation of seasonal differences. These cycles were first calculated by a Serbian prisoner, Milutin Milankovic, who ran afoul of the Austro-Hungarian Empire at the start of World War I and was imprisoned for most of the war. I guess they were kind enough to give him pencil and paper. And so using calculations that were understood, at least in principle, from Newton's gravitational model for the solar system in the 17th century, Milankovic actually calculated all these perturbations that the moon, the sun, and the other planets would have on these three parameters: the precession of the Earth, the amount of tilt of the axis, and the shape of the ellipse. And he predicted that there should be cycles with periods of 23,000, 40,000, and 100,000 years, as we know today. Unfortunately, he published these results after the war, when he was finally released from prison, in an obscure Serbian journal in Serbo-Croatian, and this did not captivate the geologists of the world. Indeed, it was not until the 1960s that this work was rediscovered, and modern calculations confirmed all of his pencil and paper results. It's important to note that all three of these cycles operate simultaneously, and they have large effects on global climate. It's also important to note that all three of these cycles are both perfectly predictable. Milankovic did it in his prison cell. We can do it in a matter of seconds on a computer today. And they are all completely beyond our control. The Greenland and Antarctic glaciers provide a record of climate long enough to measure the effects that these cycles actually have on Earth's climate. The ice on both the center of Greenland and in the Antarctic plateau is over 3 kilometers thick. That's a thick sheet of ice. It's formed as annual layers of snow build up and are compressed by the layers that fall above them, because it never gets above freezing, and so they never melt. For thousands of years, the individual annual layers are preserved, so one can use them as a calendar, just like the rings of a tree. You can actually count them. And if you cut away a layer, you can see these layers annually and count them down. After a sufficient amount of snow and ice builds up above them, of course, they start to get squished so close together that it's difficult to see the individual annual layers. But nonetheless, it's certainly true this going deeper always means going further back in time. And there are techniques that we can use to date layers as we go deeper and deeper into the glaciers. The bottom of the Antarctic glacier dates from over 750,000 years ago. That is, snow has been accumulating there and forming glacial ice over the last 750,000 years. Thus, by using standard oil drilling equipment and drilling down a core through the ice and pulling it out again, one has the at top annual layers and further down compressed layers that provide us a continuous history over the past 750,000 years, many times longer than the longest of the orbital cycle changes. The isotopic composition of the ice itself, just as the isotopes in the tree rings, provide us with an excellent thermometer. Recall what we know about isotopes, temperature, and the phases of matter. Water is in a liquid state, so the molecules are touching each other but free to slide around. The water containing H218O, the heavier isotope of oxygen, is, as a molecule, heavier than water containing H216O, the light and normal oxygen isotope. And thus, for the energy to be added sufficient that the water molecules touching each other are given sufficient energy to break apart and the water transfers from the liquid state to the gaseous state with the molecules free to run around, is higher for oxygen O18 than for water with oxygen O16. Thus, to evaporate the water from the ocean, higher temperatures are required to get the heavy oxygen out, and the fraction of heavy oxygen to light oxygen thus provides a measure of temperature. Now recall from Ötzi that the heavy H2O also rains out more quickly, but there's still more of it in the air when it's warm. And by the time this water is evaporated and transferred to the northern and southern regions of the world and rains out, the oxygen 18 to oxygen 16 ratio provides a thermometer that's accurate to a fraction of a degree. Interestingly, the ice also traps air bubbles as it freezes. You can imagine the snow falling down, and on a day just after it snowed, the snow is very fluffy. There's lots of air that's running around between the water molecules or the frozen crystals of snow. But as more and more snow comes over the top of it, this air becomes eventually trapped. It's like the little bubbles that you see in your ice cubes in your refrigerator. They're little bubbles of air. They're samples of the atmosphere. They're like a chemist's ampule, which samples the atmosphere and then seals it off in ice so that it's locked away for as long as the ice doesn't melt. And the ice in these glaciers hasn't melted in Antarctica for 750,000 years. Thus, sampling the air in these bubbles gives us a direct measure of the number of molecules of each type in the atmosphere, the number of CO2 molecules, the number of methane molecules, the number of nitrous oxide molecules in the atmosphere going backwards in time. It is as though we had a sampling station that was there with a thermometer measuring temperature from the oxygen isotope ratios and a chemist taking little samples in his flask of atmosphere going back over hundreds of thousands of years. The records of these molecules show the impact of humans on the composition of Earth's atmosphere. Let's look at 3 of the molecules that are most frequently implicated in the global warming discussion: carbon dioxide, methane, and nitrous oxides. If we look back over the last 10,000 years at the ice records, we see, starting with nitrous oxides, a relatively flat period from 10,000 years ago, with perhaps a slight decline over the last 1,000 years. But then, since the middle of the 19th century, a sudden rise by more than 30% in the number of nitrous oxide molecules in the atmosphere. Methane is another molecule which has very potent greenhouse gas potential and therefore traps solar radiation and tends to raise the temperature of the Earth. If we look here, we see that 10,000 years ago, the amount of methane in the atmosphere was actually falling slightly for about 5,000 years, and then rising just slightly again to about its same level until the 19th century. And then, bang, it goes up in a spike that has caused an increase of 250% of the number of methane molecules in the atmosphere for each molecule of nitrogen and oxygen. And finally, the culprit most frequently cited, carbon dioxide, again shows a relatively flat, possibly slightly declining atmospheric composition until around 5,000 years ago. But 5,000 or 6,000 years ago, a slow but steady rise begins. What happened 5,000 or 6,000 years ago? Well, of course, the beginning of agriculture and the rapid growth of the Earth's population. Agriculture implies cutting down trees. Cooking implies using firewood and burning it up, putting carbon dioxide into the atmosphere, which is not necessarily sucked out of the atmosphere again by the regrowth of a forest if you've turned it into farmland. But then, again, in the 19th century, we see this sudden, rapid spike such that carbon dioxide levels have gone from 250 parts per million, that is, out of every million molecules you sample out of the air, 250 of them are carbon dioxide, to nearly 380 parts per million today, again, a rise of more than 30%. All these molecules have the ability to trap infrared radiation that attempts to leave the surface of the Earth and reflect it back to Earth, thus increasing the temperature of the atmosphere. Now, if you're a casual observer of the global climate debate, you will think that all of this has always been a consequence only of human activity. But nothing could be further from the truth. We see this in the records from the Antarctic and Arctic glaciers. Records over the last 500,000 years show large and obviously totally natural fluctuation in the prevalence of these molecules, which coincide precisely with those Earth orbital cycles which I described at the beginning of the lecture, producing alternatively cold periods, which we call ice ages, and warm periods, which we call interglacials. It turns out there is a tight correlation between the amount of carbon dioxide in the atmosphere and the temperature fluctuations over the last several 100,000 years. This is the graph that you will want to remember. On the left side, we plot the amount of carbon dioxide in the atmosphere, ranging from a low of about 180 parts per million to a high of about 300 and some parts per million, or almost a factor of 2 change in the carbon dioxide composition of the atmosphere. That's shown in the red squiggly line, which you see bounces down over a 100,000 year period, then rather rapidly shoots up, and then bounces down again for another 100,000 years. Rapidly shoots up, bounces down again, where the wiggles correspond to about every 23,000 years, the precessional cycle of the Earth, to a minimum 100,000 years, then rapidly up, down again, and finally up to where we are today. On the right-hand axis of this graph, we plot the temperature as deduced from the isotopic oxygen and hydrogen deuterium ratios in the ice. The temperature measured because heavier molecules are more difficult to evaporate than light molecules and thus require a higher temperature. Here you see the temperature range is not, as in the last lecture, over a few tenths of a degree centigrade, but over 15 degrees centigrade, from nearly minus 10 from the average to something like plus 6 degrees. The blue line represents the changes in temperature over the last 450,000 years. And you see a striking relationship between the temperature and the carbon dioxide. Again, the temperature bounces down, shoots up suddenly, bounces down again, up and down on this 100,000 year timescale, with some wiggles in between representing the 23,000 precessional cycle, until it reaches 10,000 years ago a relatively stable plateau. An interesting fact here is that we see this striking correlation between the amount of carbon dioxide in the air and the change of temperature on the surface of the Earth. But we don't know which caused which. We can't tell from this record, because the dating is not quite precise enough, whether or not an increase in carbon dioxide suddenly warmed the Earth, or whether a sudden warming of the Earth from some other cause increased the amount of carbon dioxide in the atmosphere. This is clearly a fundamental question which must be answered if we have a hope of predicting the future of climate in a carbon dioxide-rich atmosphere. You see the point labeled today. Over the last century and a half, as you saw from the earlier figure, the amount of carbon dioxide has shot up rapidly. It is higher today than it's been in the last several million years. You will also note that the temperature has not had a similar spike. While the carbon dioxide today, if we were to believe the correlation in the past, should correspond to a temperature 6 degrees centigrade above average, we have not seen such an effect, fortunately, because a 6 degree temperature change, 10 times the temperature change that the Vikings experienced in Greenland during the medieval warm period, or the Dutch experienced in the Netherlands during the Little Ice Age of the 17th and 18th centuries, would cause drastic effects on precipitation patterns, agricultural productivity, sea level, and many other things. We have raised this level of carbon dioxide in a geologically short period of time, only a little over a century, whereas this record you see extends over nearly 500,000 years. Whether the temperature will follow the carbon dioxide up, whether the temperature will produce an increase yet still from carbon dioxide in natural sources, are questions which we must answer if we wish to truly understand and predict the future of climate. The ice also reveals other things besides its isotopic composition and the little bubbles of gas that it traps. It, for example, reveals airborne dust particles and sea salt spray embedded in its layers. When it's very windy over the ocean, the waves are very high, they break, and salt particles dissolved in the water get flung up into the air, eventually raining down on the ice caps. Furthermore, when the global climate is generally windier, when it's generally stormier, dust can travel enormous distances. Indeed, in the Greenland ice cap, we see dust which, again, from its isotopic composition, can be directly linked to the Gobi Desert in northern China and Mongolia. That's where the dust has been coming from. If we look at where the dust and salt are highest, we find that it is at the peak of the coldest periods of the ice ages. And where the salt and dust is lowest is during the warm periods of the interglacials. So if there's one piece of common wisdom I can disabuse you of, it is that stormy periods occur as the Earth warms. The ice records belie this statement. Hurricane Katrina was a strong storm, and it occurred in a period in which discussion about global warming was great. However, it is scientifically incorrect to attribute the strength of Hurricane Katrina and the damage that it did to global climate change. We know from the ice record that the stormiest periods on Earth, the periods with the highest sustained winds and the most severe storms, occur during the coldest periods. And indeed, the warm periods, such as we are existing in today, tend to be lower in stormy weather. In addition to the long-term changes, the ice core records show remarkably abrupt fluctuations in climate on timescales as short as decades. Again, by measuring down layer by layer, we can see an annual record of the climate. And we see that at times there are simultaneous changes in temperature, precipitation rate, the thickness of the layer tells us that, and the dust content, which observed on timescales far too short to be caused by any kind of change in the orbital forcings of the planets that yield the biggest changes you saw on the preceding diagram. Those are timescales of tens of thousands of years, many millennia. The timescales we see that are abrupt can occur in as short as a decade. There's a particularly striking example of this from near the end of the last ice age. As I said last time, the tree ring samples tell us that the last ice age peaked around 20 to 24,000 years ago and ended rather abruptly around 10,900 years ago. But it wasn't a simple transition from a cold period to a warm period. A little before that, as the Earth started to warm up, there was a sudden cold snap called the Younger Dryas, after a flower that grows in northern climates that is particularly sensitive to temperature, which suddenly clicked on within a period of less than 20 years, reversing the overall warming trend, which was to lead to the termination of the last glacial maximum. This cold snap lasted for about 1,500 years, and then just as suddenly reverted to a rapid warming trend. And the warming trend continued till today. We don't know what the cause of this sudden change was, but speculation centers on a disruption of the circulation of the ocean. The ocean is like a giant conveyor belt. It starts in the Caribbean and the tropical Atlantic, carrying huge amounts of warm water northward. That warm water contains heat, the energy of the vibrating molecules, and that heat is gradually released to the atmosphere. Because the Atlantic is saltier than the Pacific, and salty water is denser, as this warm conveyor belt gradually loses its energy and gets near the coast of Greenland and between Greenland and Norway, the saltiness and the coldness suddenly cause the water to be dense enough to sink to the bottom of the ocean, miles below. This cold, salty water then flows south, all the way to the South Pole, is involved in this mixmaster current that circles all of Antarctica, and is redistributed, again at depth, to the Indian and Pacific Oceans, where eventually it warms up and rises to the surface again, returning the water to the Atlantic so the cycle can continue. If for some reason that current suddenly switches off, we can expect a drastic and sudden change in the Earth's climate. For example, if there's a large influx of fresh water to the North Atlantic, such as would happen with the collapse of an ice sheet, which is after all fresh water at the end of an ice age, the freshening of the water makes the water less dense, and the sinking motion stops, shutting off the entire global conveyor. It is speculated that this can happen on a timescale of only decades, and this may be the explanation for the Younger Dryas and other similar rapid shifts in climate. The possibility of a similarly rapid change today is a leading cause for concern amongst climate scientists who look to the ice core record to refine their models in predicting the future of the planet. The ice cores provide a text more than 500,000 years old, in which we find written a log of polar temperature, a regular sampling of the atmospheric gases, and a record of ancient storms. As such, the polar glaciers provide a remarkably complete picture of climate change driven by the Earth's orbital variations, as well as of shorter-term events. However, they are, by definition, found only at the Earth's poles, and a more worldwide indicator of climate is certainly desirable. Furthermore, another major driver in the long-term history of climate is the arrangement of land masses on the Earth. To provide a global view and to extend the record back even further in time, we have to now turn to the record buried at the bottom of the sea.